Welcome to the next video on survival analysis. We will be going over how to evaluate our survival models. So let's just start with taking a look at some data. So we have one feature here, and this is our risk. And we want to figure out how well did our model fit the data. A common way to do that is to look at the C-index. And often it's exactly what we want because we care about knowing if we ordered the data correctly. Do we know that this sample has higher risk than this sample? And that's exactly what the C-index measures. So to calculate the C-index with stratified k-folds, you might be tempted to just go, okay, we have our C-index for the first test fold. We have our C-index for the second test fold and the third test fold. How about we just calculate them for each fold and then average them? There's a couple of problems with that. The C-index is not very reliable when you have small folds. So if you have small folds, this isn't a very good idea. And there's another issue whenever you have a metric that's kind of a correlation metric. Let's say this was your test fold right here, and you got unlucky, you had only high feature values. If you look at all the data, we clearly have a very strong C-index. But when you only look at high feature values or low feature values, you now have very similar feature values, and you're going to have very similar risk values. And your C-index for this test fold will be very low. And that's not specific to C-index. That happens actually anytime you have a correlation and you reduce the size of one of your features, one of your axes. Let's go to AliAxis actually really fast, and let's see this in action. So let's make some data. We'll have a normal distribution, and we'll add some noise. So we have a very strong correlation between our feature and our target here. But if we zoom in to a small section of the feature, now it appears there's no correlation between our feature and our target. So that's not specific to C-index. That happens anytime you have a correlation metric and you zoom in on one axis. Okay, so let's go back to our C-index discussion. So what should we do then if taking the average of the folds is not the answer? Well, you could just take the predictions of each fold and then calculate the C-index from the predictions. Calculate C-index one time instead of 3 times. This sounds like a really good idea, but as we discussed in our previous video, the predictions for the neural net can vary. The scale of the predictions can vary per fold. So you can't mix predictions from different folds, unfortunately. So then what do we do if we can't take the average and we can't take the predictions? What I came up with, and I don't know if this has been reported before, but what I came up with is, let's take the ranks. The ranks will be stable across the folds, and then we'll use the ranks to calculate our C-index. Now, some people are very uncomfortable with this idea because if we have our data, and let's say this is our test fold again, to get the ranks of this data, we have to look at all the data, which includes the training data. So when people hear test data and training data together, that makes them very uncomfortable, and you can't convince them that this is the right thing to do. But you actually don't need the training data. You just need any data. We just need stable ranks. So we could have just made up some new data and found out what the ranks are for these samples in this new data. And that's easy to do with one feature. You just do a line space. But that gets a little bit more complicated the more features you have. So the easiest thing to do is to just use your training data and your test data and get the ranks of the test fold and do that every single fold and then calculate the C-index one time. And instead of trying to convince people that this is the right thing to do, we can just go ahead and see if it works or not. So let's go back to AliAxis and let's see if our C-index calculation is correct. So how are we going to do that? Well, we're going to overfit with 10 features like we did in the previous video. And there's no relationship between the features and the target. And as we did in the previous video, the C-index for the train is going to be very high. And in the test, it should be about 0.5, but due to the randomness of survival data, it might be above 0.5, it might be below 0.5. So let's just see what happens. We'll have 5 folds. We'll go ahead and load our defaults, remove these, remove our bias, and what we'll do is, so that this doesn't train forever, we'll just do 100 epochs, have it stop there. So this doesn't matter. Okay, let's see what happens here. This won't take too long. And the C-index will be very high as it was before, but we're not going to let it go all the way to 1 where every sample is memorized. So here actually, so these test C-index values, this is on the test fold. So this is not a rank-based value. So this is just going to vary based on randomness as we discussed. So here, both of these test values are actually kind of high just due to randomness. And this one's low, and that one's 0.5, and that one's 0.14. This value down here, however, this is the value that uses the ranks across all the test folds. And as we can see, it's around 0.5, despite the fact that the train C-index was over 0.8 in every single case. So clearly, information from the train folds did not leak into our test ranks. Okay, so that was with 10 features. Maybe there's something specific about 10 features and it won't work when you have 1 feature, for example. So how about we try to overfit with 1 feature? We tried that in the previous video and we did not succeed. So let's try again and see if we can succeed this time. So what I did is I made data like this, where our feature is -2 to 2. And what I did is I then downloaded the data, and our data is going to look something like this. Each input feature will be some value with a bunch of decimal places. I multiplied it by 1,000. That will move the decimal place over 4 places. And then I made it an integer. And I also took the absolute value. So why did I do all those steps? This will allow us to use an embedding matrix. And because we have 500 samples and 2,000 possible values, 0 to 2,000, almost every sample will be unique. So there will be some samples that have the same embedding row, but most samples will have their own embedding row. And the model will now be able to memorize the data even with a single feature. So let's see if we can see that in action or not. I'm going to upload this data that I made. It's called encoded inputs. It again has no relationship from the feature to the target. And we can see that by going to the analysis. There is a little bit of a C-index, 0.537. And if you look at the values, as I talked about, they go from 0 to 2,000. So let's see if we can analyze this data or not, and see if this data correctly calculates the C-index. So we'll make our folds again, This time we need an embedding layer, and we need to know what the maximum value is for the inputs. It happened to be 1992 in this case. And we need our output dimension. I think I'll just do 128. It doesn't really matter too much. I just don't want too many parameters, because as you'll see, I forget to do that, flatten. As you'll see, we have 250,000 parameters here. The good news is it's very efficient despite the number of parameters. I'll have a separate video for embedding matrices. Okay, so let's go over here, compile. So this is just going to memorize the data. So it's going to get a pretty high C-index. I want it to get a high C-index. So I'm going to go ahead and use C-index as the stopping. And yeah, let's see what happens. Yeah. How are we doing here? Look at that. In the previous video, we couldn't overfit on a single feature, and now with a single feature, we're pretty much almost memorizing the data. If I would have multiplied by 10,000 instead of 1,000, every sample would have had a unique value. And look at that. So again, we overfit on train, and again, our final test C-index was around 0.5, which is what you'd expect for random data. And let's just go and look at our evals. Yeah, so these are also correct. So we've been discussing a lot about random data. We've been talking about random data. How about we make sure that our C-index works for data that actually has a relationship? So we discussed how the C-index struggles with small test folds. So let's make our test folds as small as we can. And let's not make this data too crazy. So let's do that. Submit that. Now we need to remember this value. This is the value we're trying to get. And we should be able to get this value exactly, because this is a very simple linear relationship. So we should be able to find this exact value when we fit our model. So let's split the data, and let's split it as much as this website allows us to. Each test fold will only have 5 samples. For the model, let's go back to our default FCN. Remove the bias again. I mean, this is overkill, but it's okay. Yeah, we'll use the loss. Yeah, this should all be fine. So we have 20 folds to train, but it shouldn't take too long. And the value that we're looking for was 0.679, I believe. Should have wrote it down. Let's see that the predictions are all looking good. As long as the predictions are somewhat in this same direction, as long as they're monotonic in this direction, then we're good. I don't really care too much about what happens. That one's that one got a little crazy. Okay, that's a little crazy. Okay, that's not what we wanted to see. Maybe we need to adjust some of these things. I'll just go 1 batch per epoch here. This will go a lot faster now, and it won't do anything crazy. When you have small folds like this, there's only 95 samples, you can overfit. Yes, and we got 0.679. So as long as the model didn't do anything crazy, each fold, then we're good. And we have a straight line each time, so that's great. And as we discussed, we only have 5 samples in test. So now the individual test C-index metrics, test fold metrics, are going to just be all over the place. there'll be 1, there'll be, sometimes they could be 0, that one's 0.2. So with the ranks, you can go down all the way to a single sample for your test fold, and you'll still get a perfectly accurate c-index at the end. Okay, so we saw that we can accurately find the c-index no matter how small our test folds are by using the ranks. Okay, hopefully you found that interesting. Thanks.